Hello. Today we're going to talk about kinematics, or motion without regard to mass. In particular, we're going to talk about the motion of objects moving in one dimension. There are two basic types of quantities that we like to talk about in physics. One of them is a scalar. A scalar is a quantity that basically only has size. Magnitude is just a fancy word for size. Examples of things that only have size are things like distance. We talk about how far did it go, or mass. We talk about how much stuff is there, or volume. We talk about how big it is. This is different from a vector. A vector is a quantity that not only has size, but it also has direction. So now we care about which way is it pointed. Think about when you give directions to somebody to get to your home, you'll use words like left and right, or north, south, east, and west in particular. A lot of times we use north, south, east, west, angles, things like that to denote direction. Sometimes when we do math with vectors, we like to talk about those directions, not in terms of north, south, east, and west, but in terms of plus and minus. Because if we look at the cardinal directions, or let me get a better marker, or north, south, east, and west, they conveniently fit onto positive y-axis, a positive x-axis, negative x-axis, and a negative y-axis. So sometimes we use plus and minus to talk about the direction of vectors. It's just whatever's convenient for us in that moment. So an interesting question to ask is, what is time? There are two things that we think about when we think of time. The first one is, when did an event occur? We just denote that with a letter T. And then there is, how long did this event take, right? So time has a size to it for sure. And it seems to progress forward, right? So that seemingly is a direction. However, since time doesn't appear to have a backwards direction, we tend to think of time as a scalar. And the units of time you're already pretty familiar with, right? Seconds, minutes, hours, years, all of that stuff. Most of the time we like to use seconds in physics. That's our, international system base unit of time. But time is typically treated as a scalar. I don't think I've ever seen it treated as a vector. I feel really weird. But the main way we talk about time is we talk about time intervals. How long did something last? Why do I bring this up? Well, because another thing that we like to talk about a lot are things like distance and displacement. Distance is the length of a path you've traveled, whereas displacement is your change in position. So in example, we could have an object that travels on a swirly, squiggly, scaly line, right? And it's traveled some lengthy distance, but its displacement is actually just the straight line between the two, right? So there's a difference between distance and displacement. When we talk about time, we only have the amount of time that's passed. There aren't any different ways to measure it. So it's a scalar. There's only one way that we work with it. But with distance and displacement, there are actually two different quantities happening there. There's a distance that is an amount, just the size of the path that you traveled. And then there's a displacement that is strictly the shortest path from start to finish, and which way did you go to get there? So there's kind of a distinct difference between the two that matters. Distance is a scalar, displacement is a vector. Typically we denote distance with the letter D for distance, very original, but you might note with displacement, because we call it a change in position, we use a Greek letter delta, which is just a triangle, looks like a triangle. I won't shame you if you call it a triangle, but other people are going to shame you if you call it triangle X. So delta X, or change in your X position. Sometimes people will even denote it as a delta D. People like me are lazy and just use a D for displacement and the delta to indicate that it's not just a distance. Other things that you'll notice in physics texts and things of the like is they will boldface vectors, or put a little half arrow on top of a vector to let you know that it's a vector. What's one of the important distinctions then between distance and displacement and vectors and scalars? Well, take this for example. Suppose that you walk 5 meters east. right? What's the distance that you've traveled? You've traveled 5 meters. Now suppose you walk back and you travel back 5 meters. Let me write that backwards for you. And we walk 5 meters west, right? What's that distance that you've traveled? You've also traveled 5 meters. Your total distance traveled here is 10 meters, 5 meters to the east, 5 meters to the west. Your total displacement, though, is 0. You started right here. You ended right here. You've achieved 0 displacement. So there's an important distinction between vectors and scalars. When you change direction, your vector quantity could be different from your scalar quantity. And that's going to matter for things like when we're trying to figure out how fast are you going. So why does all this stuff about distance and displacement and vectors and scalars matter? Because we eventually want to talk about how fast somebody is. People make money out of being fast, right? So if we consider how fast something is or the speed of an object, the two things we typically consider are distance and time. If you take 2 runners and you have them both run a 100-meter dash, the person that covers it in the shorter time is the faster person, right? So speed depends upon your distance and the time it takes you to travel there. But if we're measuring over a reasonable time interval, then we're actually taking an average measurement. Anybody that's run a track event knows that you will speed up and slow down as you go throughout that race. You'll blast off the block, you'll reach a steady pace, and then you'll push at the end. You'll get a lot faster towards the end, especially on a longer distance race. So that's your instantaneous speed. So speed is basically how fast you're going on average. But if we want to talk about instantaneous speed in your car, that's where the needle is pointing to in your car, right? That's an instantaneous velocity what the needle is pointing to in your car, or an instantaneous speed, what your speedometer is pointing to in your car. That's why it's called a speedometer. Why is it not called a velocitometer in your car? Because velocity is a vector quantity. It has direction attached to it. For the most part, if you don't change direction, your instantaneous speed and your instantaneous velocity will have the same size. But if you are running, so if you're running towards the west at, say, 10 miles per hour, right? You can say that your instantaneous speed is 10 miles per hour. You can also say your instantaneous velocity is 10 miles per hour west or negative 10 miles per hour. All right. And your speedometer doesn't tell you negative things. So it's not a velocitometer, it's a speedometer, right? Also interesting, if you're running a track event like the mile, well, maybe not the mile, but the 400 meter, if you make a complete circuit around your track, you have no displacement. Your velocity is a rate of change in position with respect to time. It's not just how fast you're going. Instantaneously, it's how fast you're going and in what direction. But it's a rate of change in position with respect to time. If you have no displacement, if you end where you started, then you actually have no average velocity, because over the course of traveling around a track, you traveled in a positive direction and a negative direction and a positive direction and a negative direction until it all averaged out by the time you got back to the beginning. So vectors and scalars have important differences between them. Velocity and speed have important differences between them. Important to note, though, velocity is a rate of change in position with respect to time. Velocity and speed are instantaneously the same size. Velocity is basically speed with direction, instantaneously. I want you to consider the speedometer in your car. The speedometer in your car gives you instantaneous information about how fast you're going in that moment. But if you were traveling to school and say it was about 5 miles away and it only took you a fifth of an hour to get there, so 12 minutes to get there, you could calculate your average speed over the course of the trip, right? It wouldn't be that hard. Your distance over time, 5 divided by 0.2, right? 25 miles per hour. Not that hard to calculate your average. But we know that along the way, you might hit traffic lights, you might speed up, you might slow down. So your instantaneous speed might change, but your average is just an overall calculation. So your instantaneous speed may change, but your average is a calculation over an entire time interval. So things to think about. If an object's velocity is constant, is its speed also constant? If you're going 5 miles per hour, 5 miles per hour, 5 miles per hour east, what's your speed? It's also 5 miles per hour, right? So if your velocity is constant, your speed is also constant. Velocity is basically speed with direction, right? But if your speed is constant, does your velocity have to be constant? Are there situations where, say, an object is rounding a corner at 5 miles per hour, or more likely 15 miles per hour, 15 miles per hour, 15 miles per hour, and it's going from north to east, and its direction has changed, but its speed has not? Absolutely. Right? There are situations where your velocity can be changing, but your speed is constant. That's when you go around a curve. So one of the things that I really want you to take with you is the idea that velocity is a rate of change. And something else that's a rate of change that you've learned about in your math classes is slope, right? So if we consider this object, and I've drawn it on a position versus time axis, and you might be looking at that saying, position versus time, that's weird, right? X is for position. I know it looks weird compared to your math classes where it's always Y versus X. And then you might be looking at it going, but it's not a coordinate axis because there's no third and fourth quadrants. We only have quadrants 1 and 2 on that graph. Well, we can't have negative time. And that's why our graph ends up looking like just half of what you deal with in your math class. But so slope is a rate of change. Velocity is a rate of change. So now I want you to consider this object. It's moving, not at all. It's maintaining the same position the entire time. It has no rate of change, so it has no velocity. This object, however, is moving. It's moving in a positive direction away from where it started. It's moving steadily. I can tell because it has a steady slope, right? A steady slope means a steady rate of change, which means it has a steady velocity, right? Positive slope, positive velocity, steady slope, steady velocity. This object also has the exact same rate of change in position. It began at a different spot. It will end in a different spot, but it has the exact same rate of change. This graph has an object moving at a steady rate of velocity, a steady rate of change in position, right? It's moving in a different direction though. It's moving towards an origin instead of away. And so its velocity is steady, it's constant, but now it's negative. This object has the exact same rate of change in position, but it started in a different place and ended in a different place. Which of these two objects is faster, the dotted line or the solid line? You can tell that the solid line has a steeper slope, and so it's faster because it has a higher rate of change, right? So these are some of the things that I want you to think about when you think about motion, when you think about graphing. Our calculus classes teach us things like increasing and decreasing and concavity, and none of that tells us anything about motion. I want you to use words like speeding up, slowing down, moving away, moving towards, getting faster, getting slower, being faster, moving at a constant rate, or moving at a changing rate. Those types of things. Use plain English, not calculus, to talk about what objects are doing. Acceleration is a change in velocity with respect to time. It is a rate of change. The same way velocity was a rate of change in position, acceleration is a rate of change in velocity, which means it's also a slope, but it's a slope of velocity, whereas velocity was the slope of position. You can replay that a bajillion times if you want to until you get it. We measure it in meters per second per second. I will say meters per second not meters per second squared, because we know that a distance is a meter, and we know that an area is measured in meters squared. Time is measured in seconds, but there is no physical quantity that's measured in seconds squared. So there's no such thing as seconds squared. I will emphasize meters per second when we talk about these things, because it is a velocity with respect to time. It's a rate of change in meters per second. You are welcome to say meters per second squared. I'm just letting you know that I won't. An instantaneous acceleration is kind of a jerky ride, right? That is not a smooth getting faster. That's like when somebody is shifting gears in a stick shift car and it goes, and you can feel yourself jerk back and forth in the car, right? That's when your instantaneous acceleration is changing. In kinematics in one dimension, we don't deal with a whole lot of that. We tend to talk about constant accelerations the whole time. Acceleration is a vector quantity. It has a direction to it. If velocity is a vector and acceleration is a rate of change in velocity, then acceleration is also going to be a vector. One of the ways that I like to think about acceleration is in terms of how fast you get fast. It is a rate of change in velocity. So it's how fast you get fast or how fast you get slow. So you can be at a red light, it turns green, and you gradually make your way up to your top speed. Or you might slam on that gas pedal and get up to top speed as fast as you can, right? You hear that car going, trying to get up to top speed. And that's okay, whatever makes you happy. Both of them are accelerations. Both of them are changing your velocity. But at the same time, changing your velocity to slow down, how fast you get fast or how fast you get slow, is also acceleration. So if you're coming up on a red light and you know you have plenty of time, you might just gently press on the brake pedal and gradually work your way down to stop. So acceleration is rate of change in velocity, how fast you get fast or how fast you get slow. Worth noting though, it's pretty much anytime you change motion. If you change direction, if you get faster, if you get slower, all of these are accelerations. Anytime you change your velocity, you are accelerating. Okay, so an interesting thing to consider is these red, green, and blue cars. One of them is not accelerating. Take a really good look at that video, and you can replay it a couple times if you want to, and figure out which one of these is not accelerating. And then take a look at it and figure out which one of them is accelerating more. Right now, I've put some dotted lines on this thing so that we can kind of see better the pace at which they're going. But you can see that the red car is moving at a steady pace every frame, right? But the green car begins at the same spot as the red car and then is suddenly behind the red car, but by the end has caught up to the red car. This indicates the green car is in fact accelerating, but the blue car just beats everybody, right? That doesn't necessarily mean that the blue car is accelerating, right? It could just be going at a higher average velocity. But if we really take a look at that diagram, we can see that it's actually covering more distance with each frame. All right, so consider this. If you are changing your velocity, you are absolutely accelerating, right? Can you change direction and maintain a constant acceleration? Think on that one for a minute. Consider throwing an object into the air, right? Throw an object into the air, shoot, just like that. It changes direction. Did it maintain a constant acceleration? It turns out, yes, it did. This cute little mouse here, as soon as it left my hand, it was in free fall. Free fall is motion under the influence of gravity alone. Nothing else is affecting it. While this is in my hand, it is not in free fall. But as soon as it leaves my hand, gravity takes over its motion. Near the surface of the earth, Objects move at a steady rate of 9.8 meters per second every second. This means that an object that is dropped will begin with 0 velocity. But after 1 second, it will be moving at 9.8 meters per second. After 2 seconds, it will be moving twice as fast at 19.6. And after 3 seconds, it will be moving 3 times as fast at negative 29.4 or something to that effect, meters per second. It increases by 9.8 meters per second every second. Notice I've drawn more distance in between each of these 1 second intervals as well. If we're faster as we go, we can cover more distance each second as well. This is true for all objects near the surface of the Earth. So consider that object thrown up into the air. When it's at its highest point, how fast is it? It stops for just a moment, right? It stops for just a moment. But what's its acceleration at its highest point? Is that also stopped? Let's think on that for a minute. Acceleration is a rate of change in velocity with time. So if you throw an object up into the air and it stops and gravity goes away, there's no more gravity, no more acceleration, that object should never come down, right? If an object is stopped and it has no acceleration, there's no more change in its motion. It is just stopped now, forever. That doesn't seem to make sense. What goes up must come down, right? So what's actually responsible for gravity? What's responsible for gravity is the mass of the Earth and the distance that the object is from the center of the Earth. When this object reaches its highest point, does the Earth go away? No. If the Earth doesn't go away, why would gravity go away? So while an object stops at its highest point, it doesn't actually lose its acceleration. It is actually maintaining a constant acceleration of 9.8 meters per second due to gravity. So we have to talk about this other pesky thing with acceleration, which is scalar and vector terms. The vector term for acceleration, because acceleration is a vector, is acceleration. The scalar term for acceleration is also acceleration. We didn't come up with a different one. When an object is speeding up, it's accelerating. When an object is slowing down, it's also accelerating. When an object is changing direction, it's accelerating. Anytime it changes velocity, there is acceleration. But somewhere along the way, we came up with this term deceleration. And deceleration strictly means slowing down. It's a scalar term. It means you're losing speed. Doesn't mean you're losing velocity. It means you're losing speed. Decelerating does not necessarily mean that you have a negative acceleration. Objects can slow down and have negative accelerations. They can speed up and have negative accelerations. So when are we speeding up? When your acceleration is in the direction of motion. If you want to get something moving faster, you're going to push it in the direction it's already moving. When is an object slowing down? When you push against its motion, when acceleration and motion are opposite to one another. So when you want something to stop moving, you're actually going to push against the direction that it's headed, right? And then when is it going in a curve? That's when we're changing direction. We're maintaining speed, but still accelerating. Uniform circular motion or centripetal motion is one thing that we may end up talking about here and there throughout the next couple of weeks. But uniform circular motion is something that happens when acceleration is perpendicular to motion. So if your velocity and your acceleration are headed the same way, you'll get faster. If your velocity and your acceleration are headed opposite ways, you'll slow down. And if your velocity and your acceleration are perpendicular to one another, you will actually end up changing direction. All right, so how do we accelerate an object? Think about it with a car, right? You can slam on the gas pedal, you can slam on the brake pedal, you can turn that wheel. There are 3 separate accelerators in a car. There's the gas, the brake, the steering wheel. Those are all accelerators. What I want you to think about is the fact that for every one of those, when we change direction, we are accelerating, we are in fact changing velocity, but for every one of those, we're forcing a change, right? If we slam on the gas, we're forcing the engine to rotate the wheels faster. If we slam on the brakes, we're forcing the engine to slow down the rotation of the wheels. If we turn the steering wheel, we're forcing the wheels on the car to change direction. Every single time we accelerate, there is an action that forces that to happen. The things that I want you to take from this today are that velocity and acceleration are both rates of change. What you're going to work with in lab is actually taking a look at those rates of change on a graph, that when an object accelerates, its acceleration is a rate of change in velocity with time. It's the slope of a velocity graph. When an object is moving at a steady velocity, the slope of its position graph will tell you its velocity, right? So velocity and acceleration are both rates of change. The other thing I want you to take with you is that anytime you are accelerating, your velocity is changing. You cannot remain still and be accelerating. You can have a steady speed and be accelerating, but you cannot stay still, right? You can stop for a moment. You can throw an object up in the air. It will stop for a moment, for an instant, and it'll come back down. But it cannot stay stopped and be accelerating, because acceleration is a rate of change in velocity. Your velocity is constantly changing. And objects do not spontaneously accelerate. Something is forcing them to do it. In a car, there are very mechanical things that we're doing to force it to change. When you drop an object, what's forcing it to change? The earth is pulling it down, right? So acceleration doesn't happen just because. Acceleration is the result of an action. Acceleration is something that is forced to happen. Acceleration is a change. So hopefully this sets you up for lab. Hopefully you guys have a little bit of clarity in how to talk about these things. Don't get embedded in math terms. Make sure you use plain terminology like speeding up, slowing down, changing direction, and hopefully you learned a little something today. Thanks very much. Bye-bye. Up to speed, or you can just pull out from that stoplight and push your pedal or push your foot on the gas and go as fast as you can. Stuff about distance. Okay, conveniently fit onto, wow, I put my X and Y backwards. That was terrible. Take bajillion. Take bajillion. Okay. Which is, wow, that's the worst delta I've ever drawn. Faster. That's like when somebody is shifting gears in a stick shift car and it goes, and so when you're giving directions to somebody, it matters that you say north, south, east, or west. Whereas if we're just talking about, do you want another helping of ice cream? It only matters how much ice cream there is. It doesn't matter what direction the ice cream is headed in, because, well, that's a terrible example. I guess we would want the ice cream to be heading into our mouth. Or a little kid might run out in the street in front of you and you slam on that gas pedal and you get to that stopped speed very quick. Or a little kid might run out in the street in front of you and you slam on that gas pedal and you get to that stopped speed very quickly.